I just got to get this out of the way. So I'm Andrei Neagu. I work as a software engineer, and I've been using Python since 2013, and I'm an enthusiast about Python. So in this talk today, we'll talk about a use case for shared memory, and the problem at hand is that we have an application that is based on, uses sliders to acquire information, and it has to process it in real time. So you have multiple sources of data coming from these lidars. If you don't exactly know what a lidar is, it's a device that actually spins, or that has a laser which spins around, and to give you the information of the depth of a point. So you can actually use it to detect objects, and they use it in self-driving cars, or for all sorts of different types of applications. So you require multiple stages of processing this data. You have to analyze it. You have to use a lot of algorithms on top of it. So maybe a processing pipeline for this may look something like this, where you're going to have your input devices which acquire data, put it inside a store, and then you'll have some, let's call them workers, which maybe initially get your data, clean it up, try to cluster it around, apply maybe cluster pattern recognition, tracking, etc., and do other things with it. And then once you have maybe a bunch of clusters, you can see how some shapes are moving around and other things. And some possible approaches for this problem could be async I/O, threading, and multiprocessing. But because you're handling a lot of data, which are tens of megabytes of data, async I/O isn't really an option. So you could just keep it all together. We could try to use threading, but it has a problem, which is the GIL. But let's just look at threading a bit. The pros of threading is that you can share memory. Can you still hear me? Yes. You can share objects in a secure way between threads. You just have to use locks, so you don't have to move data around that much. And because you're using a lot of data, you would not like to move that so much data. And you have a low setup overhead. And the main con is the global interpreter lock, which Python is so infamous for. So an implementation with threading may look something like this. It uses a queue. The queue is this is like the main way in which you could use this. Sorry for, I got a bit emotional. It's my first time speaking in public, so I got, thank you. Okay, so I basically use this pattern on dozens of times, and like in 90% of cases, it gets me out of situations where I need to use concurrency. So this is the recommended way to use it. Another way to use threading could be like this. You could use locks to manually lock and manage your data structures to avoid concurrency problems. And this is one situation that we could also encounter. So let's have a quick look at how the GIL operates exactly to have a better understanding. So in this situation, you may see that you have 3 threads that run in parallel. Okay. So while thread 1 runs, it acquires the global interpreter lock, which is basically a lock. And while this is acquired, nobody else, no other thread, can use our interpreter at that time. So even though thread 1 and thread 2 are scheduled at 2 different processors inside your CPU, the code will still get stuck. So only one thread at a time you will have executing. So if you're using, so you have multiple workers, and each needs to process in parallel a lot of data for your task, this is not a good idea. So you need to look at something else. But first, Please do not dismiss threads because everybody says they are bad. I actually use them a lot and had great success with them. So think about your use case each time you have to use each time you have to create a new application. So, and that will help you quite a lot. And now let's go on to multiprocessing. And so the first pro that comes to mind is that you don't have a GIL anymore in multiprocessing, because it's not that you don't use it anymore. It's still there, it's still getting used, but you're just using the main thread of your process to do all the work. And the cons is that your memory is not shared as before when you used threads, and you could just use locking. Is this better? Can you still hear me? Okay, I'm sorry about that. I'll fix it for the next talk, okay? I promise to you. Okay, so memory is not shared. I was saying that memory is not shared. This means that you need to, in some way, to copy your memory from each process to another process, okay? So you need to use inter-process communications techniques. And another con could be that you have a high setup overhead when you create a new process, okay? So you have to fork it, create it, copy memory. But for example, in some cases, maybe you would want to create a worker that downloads a web page and does maybe one or a couple of seconds of computation on top of the data it acquired. So in that case, I could suggest using a process pool, which does all the setup for you in advance, and you can just run a task on side of the process pool, and you can handle the overhead. So it is now a good time to talk about options on how to transfer your data from one process to another. For this application, for my application in this case, I evaluated a couple, which was network, multiprocessing queues, which are different from the queues you used in threading. You have to import them for multiprocessing, and of course, shared memory. So this is an example how you would use a process for multiprocessing. It's the same as thread, as the thread usage. And the Python is really cool that it enables you to experiment a lot with what you're doing just by changing a couple of lines. You replace process and the import to queue. And at this step, we can talk about data serializations. So when you're trying to do something like this, you have to understand that you are going to put your data structures inside of a queue. This queue actually uses cpickle to serialize and deserialize your data. So maybe some of you already know, but cpickles may not be like the faster data serializer out there. So this is the performance for cpickle. In my application, I have maybe, while using one single LiDAR, I have, which runs, will create 1,400 data points. Each data point is represented by 3 floats. So one single scan of a LiDAR could be something like roughly 405,000 floats in memory. So I was trying to, what I'm showing here, I'm trying to marshal and unmarshal, so serialize and deserialize an array of floats, and I was timing it against different libraries. So you could consider using maybe pickle, message pack, UJSON is UltraJSON, I guess, and JSON. The standard library is JSON. So we can clearly see that maybe pickle is not the best choice for you. So instead of using like this pattern with the queue, maybe you could use something like message pack, and not message pack, sorry, like ZeroMQ. If anybody knows what it is, already used it, it has a similar pattern like the queues one. It guarantees for you an interface similar to the queues, and it has a couple of patterns like pub, sub, etc. But basically, you can use it as a drop-in replacement for queue. And but now you could also use because you're using message pack, you can change your serializer and try something that could be much faster, like message pack. Okay, so message pack, you can clearly see that it's like it's very, very fast. And my LiDAR in my application runs at 50 hertz. And what I'm trying to transmit to you here is that for each 1 second of real time that has passed, I would need exactly almost 0.2 seconds to deserialize my data, which I'm moving from one point to another. Okay, because if you can remember the slide I showed before, you have a central storage, and you have to move data from that storage, which resides in a process, to another process which has to do something for it. So that other process will lose approximately 20% of its time. So by this time, I was thinking, oh, this could work. Maybe I made something that is smart enough to have a good result. So then afterwards, a colleague of mine came and said, hey, look, we have this cool new device. It's so little, it's smaller, it's better, and it has a screen that can show you messages, what's going around. But it has an angular resolution of 0.01 degrees, which is like the previous version. The LiDAR had an angular resolution of 1 degree. That meant you have 252,000 data points instead of 1,500. And now you need to move them all, because with higher resolution, you get a better idea of what's happening around you. So, of course, I tried to see what happened. And then, because if I'm using three points for each float, you kind of get the idea that something went horribly wrong here, because I was using actually 15 seconds for each second of data that was transmitted for each second of processing that I had to do. I was using 15 seconds just to serialize my data, so something was utterly wrong. Nothing could have ever worked. So this was not a solution for me. And we have to look at something else. So the idea behind everything is that you should try to do as little work as possible with your data. Keep it in the simplest format that you have. So don't try to do any fancy things, like if you have points, don't wrap them inside a tuple, for example, for these types of application, because that's going to cause issues to you, because you're going to use CPU time for those precious operations. And a better solution could be just put them inside a huge float buffer, and then share that with shared memory. And that's what we're actually going to do. So shared memory, it's quite simple to use. This is an actually working example that does absolutely nothing. It just allocates a raw array of doubles. There is 1,000 elements long. So you would like to use, when you're using shared memory, you use it together with C types, because shared memory is something that requires for you to have typing. It's something that's handled by the operating system, and Python just puts a simple interface on top of it. And for this situation, you want to allocate enough memory that you think that you're going to use, and then you have to keep track of how much memory you're going to need to use. That's why you have a data that's a raw array, and there's a raw array value, which is the size of the data. So in order for us to use a float and keep track of at what point we are, how big this data is, you need to have at least 2 variables. But we're not using queues anymore, you might have noticed at this point. So nothing manages for you your shared memory automatically. You have to manage locking manually. And one example of code that actually we have in our production application is this one. It's called the shared memory atomic double array. It uses a recursive lock, which is actually a lock that a process can acquire multiple times, and it won't block. But as soon as it releases this lock, another process can acquire again the lock and can do something with your can use your structure. And of course, you have to protect all sensible bits and pieces of your code with locking. And you end up with something like this, maybe. You have the classical producer-consumer problem, where you may see that you have your shared memory buffer to which you write, and then you have a reader that fetches data from somewhere. It puts it inside this store, and there's the worker which uses it. So I kind of cheated a little bit here, because this is like very. It's not a general purpose approach to this solution, because if you need to use more complex data structures, or if you need to use all your data, you don't care if you miss a bit of your data, this is not the correct approach for you, because what am I doing here? So in pipelines that when you're using like pipelines for self-driving cars, that this is inspired from that, you have your sensors that run at a certain frequency, let's say 100 hertz. They acquire a lot of data from the environment, okay? Then you have another stage that processes this data and transforms it in something more useful, okay? It clusters the data, let's say. That thing maybe won't be able to run at 100 hertz. That system will run maybe at 50 hertz, okay? Let's say 80. Then you have another piece of software that goes around there and says, okay, I'm going to tell you where inside the map am I located. So that sensor, that system will be running at 30 hertz. So in this case, I could also do something like that. I don't care about how many pieces of data I'm missing. So it actually works. And which are some possible downsides of this? One obvious thing that comes to mind is that you cannot distribute processors across multiple machines, because shared memory is local to your current machine. Another one is this solution doesn't work on the Windows operating systems, because when using Windows operating systems, Python abstracts the shared memory of the OS and uses serialization over it. So you have to be aware of this problem. And of course, you have to manually handle your data structures, and writing good data structures that are fast performing with locks is very, very hard. I don't advise you doing that. I'm not capable of doing it myself. So in the end, basically, we got a working solution. But I didn't tell you how better it was in respect with the others. We actually managed to have almost 0 to none CPU overhead from using shared memory with respect to not doing anything. So if your process doesn't do anything, you will see a 0 CPU utilization, and you can have the entire CPU cycle available for data processing and for all your important tasks. That's the main advantage of it, even though you are moving a lot of data across from one process to another. Okay, thank you. That was all I had.
If you have any questions, please raise your hand. I will come to you and give you the mic. Okay.
Hello, thank you for the talk. I just want to ask, in the pipeline picture that you show, if I don't recall if it was unidirectional. So if
just let me get to it.
Yeah.
Okay. This one.
Okay, so it was unidirect. So you don't have in this case kind of a communication channel between the worker and the store.
Well, I wasn't so fair in drawing this because I'm a very bad drawer, but actually the store itself, because all the data we're using is written to shared memory. Everything is shared memory, so the communication between W1 and W2 can happen. It's like many communications. So everybody can write and read from the same store because you just pass. we have an object in which we put all our shared memory containers, and then we pass that object to to all our workers. So everybody has access to the memory and can read and write to it whenever it wants.
So
that was our solution for that.
Signaling communication is handled through logs on the shared memory. Okay.
Yeah, that was. I will repeat this again. That's because we have the advantage that we can read the data in every time that we like and don't care too much about what happened before. Okay. We care about it, but not that much.
Okay, thank you.
Okay.
Hi, thanks for your talk. I actually never used shared memory for improving performance. Also for the backwards that you said about the possibility of not possibly horizontally scaling the processes. But I'm actually not sure about this. But did you ever think about, for example, instead of using shared memory and implementing all the locking mechanism by yourself, trying to use, for example, DevSHM in order to mount the file system into the RAM, so that I think that it should, from the high-level perspective, quite solve the same thing. But my doubt is if you explore that, if it in some way provides you the capabilities of, to do the locking mechanism that you implemented in Python at software level, if it is actually implemented by the kernel itself. I don't know if mounting the disk using DevSHM in memory in order to speed up the thing and having the shared memory could have saved you the fact that you had to implement it by yourself.
Okay, so I never tried that, but I can tell you that I have in my system a data logger which acquires all my data that I'm recording from my devices, and that writes to file system, and that's a huge issue. With certain frequencies, I see that I skip some data frames. Okay, so I have something that measures that, and I think that going through the file system is not such a good approach, maybe for this situation, because the file system is much slower than your RAM, actually, than your memory. That's Oh, in RAM. Oh no, I never tried that. I think I'm gonna have a look at that. Another idea I had, but never tried also, I just saw it last night, was to using Redis or something like that. And the speaker previous to me, which is Alexandro Molina, if you've seen his talk, he showed how you could use the memory manager that's also part of multiprocessing, and that could also be a feature. But when I was implementing this, I discarded that using the memory manager, and I can't remember why at the moment. If I think of it, I'm going to get back to you.
Hi. In your examples, there was just reading and writing data.
Yes.
Did you happen to have to need to update and delete the data to make all the CR/UD actions? And if so, does it complicate the shared memory process a lot?
So I don't know. You could do that. I don't know about performance over that, so I have no idea about performance. But here you can see that you're using array.array.doubled, okay? So that creates an array inside your memory. You can use that to change your data and then write it back again. So when you use your read data, it locks your data structure, it creates a copy and gives that data back to you to use. So you use it there, you change everything, and then you write it back. It's basically, so the data producers usually use write data, and they write data at a very high frequency inside this shared memory space. And I didn't have any issues.
Regarding DevSHM, I used it in the past, and you have probably two side effects. First one, you have to serialize toward the file, and this could be a problem if you're using custom classes, because you have to, I don't remember the magic methods, but basically you have to add the magic methods for serialize and serialize like you would do in Pickle, and this could be costly. This is also a problem if it's simple to serialize your specialized class into the file, but then you have to create a custom class. You are serializing exceptions, for example, and this is costly. Regarding the manager, the multiprocess manager, it's not cost-free. It has a bit of logic and does some conversion in that kind of in-memory database. So if your main issue is speed, probably it's better to create some kind of class or mechanism suiting perfectly your needs, because you're probably paying more. Regarding the SHM, the kernel is usually very conservative, and as soon as you start using writing and reading often, you have to tweak the kernel parameters, or it starts consuming lots of RAM and pre-allocating RAM. So for Linux, you all of a sudden see that the pre-cached memory starts rising, and probably your swap, it starts to pre-allocate swap, and this gets bogged all down. The nice thing about shared memory is if you use a shared file system between machines, if you have large chunks of data, so you can send the message about the ID of the file on the file system and share the file toward all the machines using a network file system. But make sure to use something fast, like NFS. Don't use SSHFS because, or Fuse or user space system, because they are really slow.
I guess we're done then.
Yeah.
Okay.